Okay. Hello, everyone. It's a great honor to speak here. Thanks, Professor Tawfiq Mansour, for giving me this precious opportunity to share my recent work. This work focuses on some paired statistic arbitrary permutations and the cat and sheet polynomials. It's a joint work with my advisor Zhitong Lin and Sherry Yan. First of all, some basic definitions are necessary. We say a permutation avoids pattern P if there is no subsequence whose order is isomorphic to P. For example, take W1 equals 32541. The sequence of letters 341 has the same order as pattern 231. So we say W1 contains pattern 231. However, W2 does not contain this pattern. It voids. It's well known that 231 avoiding permutations, which are the focus of our study, are counted by the famous Catalan numbers. Now we introduce the important statistic in this talk. In 2005, Kitar proposed a new statistic, the maximum number of non-overlapping descents, when studying the partially ordered generalized patterns, abbreviated as MND. Two descents I and J are considered overlapping if they are adjacent. MNA denotes the maximum number of non-overlapping ascents, and they provide this generating function for MND over all permutations by using partially ordered generalized patterns. Recently, in collaboration with Jing, they proved that MND and MNA are symmetric over 231 avoiding permutations and derived the counting formula for MNA. This formula refines the Catalan numbers. Then they also proved the distribution of MND and MNA over each of these three restricted permutations are the same as 231 avoiding permutations. By taking the complement and inverse of permutations, in 2010, Bernardi and his co-authors derived the distribution of descents over 3-to-1 avoiding permutations, which is equivalent to the distribution of MND, since all descents are non-overlapping. Building on this, Kitar and Jing posed the following open question. What's the distribution of MNA over 3-to-1 avoiding permutations? To address this problem, we use this formula, transform MNA into a petty statistic odd assigned rounds, which counts the number of assigned rounds of odd lengths. Since the MNA of permutation pi equals sum of MNA of all assigned rounds, and each round's MNA equals the floor of half its length. This allows MNA to be further expressed as half of n minus the number of odd assigned rounds. In this way, the open problem above is reduced to studying the distribution of odd assigned rounds over 3-to-1 avoiding permutations. Moreover, since the number of descents equals odd assigned rounds plus even assigned rounds, we further consider the joint distribution of odd assigned rounds and even assigned rounds on 3-to-1 avoiding permutations to refine the results of Bernardi. In order to solve this problem, we use Craig-Sanders bijection, map 3-to-1 avoiding permutations to deck paths. Then G can be interpreted as a generating function of deck paths with respect to the number of odd and even segments. Refine the deck paths into three subclasses and use the first order decomposition of deck paths. We derive a system of recursive functional equations. By computing the Grobden basis of the resulting system of functional equations in Maple, we proved that G satisfied a degree 4 algebraic equation. When y equals 1, G reduced to the equation satisfied by the generating function of odd assigned round. After that, we asked ourselves what more can be done. Our attention turned to these refined Catalan numbers. We find that the numbers of 3-to-1 avoiding permutations for which MNE equals K is counted by these refined Catalan numbers. MNE is a number of maximum number of non-overlapping exceedances. In fact, it has some other interpretations on many objects, such as band trees, deep paths, and plane trees. It counts the ones with unknowns for counts the ones with unknowns for which the statistic x equals k. X is a band tree statistic defined by this sum, where L1, L2, L3 record lengths of all left chains in T. Y can be defined similarly for right chains. Analog to MNA, X can also be transformed into a pretty statistic old left chains, which counts the number of left chains with old lengths of T. Y can be transformed into old right chains. These two symmetric parity statistics are related to the Jacobi elliptic functions and the Catalan-shaped polynomials. Jacobi elliptic functions are important. Schulenburger was the first to focus on the combinatory interpretation of the coefficients in their Taylor expansion. In 1980, Vienna defined a height statistic on Jacobi permutations, which provided the first combinatory interpretation for these coefficients. Later, in 1989, Frederick gave a simple interpretation as generating function for doubled permutations, which was proved by using continued fractions. Then in 1977, she defined polynomials as using these three derivative operators, which later be called shaped polynomials. He discovered that the coefficients of Jacobi elliptic functions can be characterized by the coefficients of shaped polynomials. See from the table, the coefficient of sen correspond to the first column of all degree shaped polynomial coefficients. And where the sen correspond to the first row degree of even degree shaped polynomials coefficients. So shaped polynomials can be viewed as a generalization of Jacobi elliptic functions. In 1979, Dumont provided the first interpretation of the shaped polynomials, describing them as a joint distribution of number of odd cycle peaks and even cycle peaks over all permutations. In 2021, Lin and Ma offered a new combinatory interpretation in the terms of increasing chains, which can be viewed as the generating function about these three parity statistics. Additionally, they introduced a weakly increasing trees model labeled by a multiset. It unifies the conception of band trees and plane trees. Analog to the shaped polynomials, they naturally introduce these multiset shaped polynomials on weakly increasing trees. They also extended the increasing band trees to weakly increasing band trees on multisets, which are in bijection with weakly increasing trees. In 2024, we proved that multi-shaped polynomials can be interpreted as a generating function for weakly increasing band trees about these three statistics: the number of even chains, odd left chains, and odd right chains. If we take N1s as M, the weakly increasing band trees degenerate into band trees. We call the special polynomials Catalan-shaped polynomials. It's the generating function for number of odd left chains and odd right chains on band trees, as well as statistic X and Y over band trees. Since the statistic M and D on 231 volume permutations and the statistic M and E over 321 volume permutations share the same distribution as X over band trees, we aim to seek statistics such that the joint distribution of M and D and ST1, M and E and ST2 both match the distribution of XY over band trees. If success, this will provide 2 new interpretations for Kaplan-Sheet polynomials. And we find that the statistic M&A of inverse of pi can meet all requirements. This theorem is crucial for our later work. We prove this using a new recursive bijection based on the first letter decomposition for 231 Ward implementations. The difficulty with this bijection is that after the recursion, we need to do a recursive transformation on the tree to complete our proof. Additionally, we find another statistic, the maximum number of non-overlapping weak exceedances, abbreviated as MNW, over 3 to 1 Ward implementations. The pairs MNE and MNW has the same distribution as this pair MND and MNA, where pi is a 231 Ward implementation, sigma is a 3 to 1 Ward implementation. Our proof uses the pair of non-intersecting lattice paths as a bridge to construct a bijection from 231 Ward implementations to the 3 to 1 Ward implementations. Under this bijection, the statistic descent and ascent are exactly mapped to the exceedances and weak exceedances, respectively. This completes our proof. The first bijection is an improved version of the bijection used by Vienno and Privy Retail. And the second is use the bijection opposed by Lin and Fu. And finally, we found an unexpected result. We found the set of the values of the lab peaks have the same distributions over 3 to 1 Ward implementations and 231 Ward implementations. And so that's all I wanted to share with you. Thank you.